Now, let's look at testing our code. So testing the feature logic, testing the feature pipeline, so integration tests for feature pipelines, and how we can do that. And we're going to start by referencing a well-known paper that was quite a long time ago, from 2017, so a bit ahead of its time. Sculley, who is a well-known researcher in the systems ML field at Google, so he wrote, and his team wrote a bunch of different tests that they saw as necessary for putting machine learning in production. So we'll just go through them, and many of these are still very valid today. So let's look at the feature test. So the feature test suggested were look at the distributions of the individual features and see if they match your expectations. We're going to look at that later on. So when we're writing new features, if, for example, we have the height of a user, and if it's not a normal distribution around 1.75 m or 1.80 m for males, well, then you might say if it's like 3 meters, they say, well, there's something wrong here, right? So that's not a good height for a male human. You might want to also look at the relationship between each feature and the target to test to make sure that something not unexpected happened. You might want to have a test to make sure that the cost for computing a feature isn't too high. So you can have something called a performance regression, that maybe somebody changes how a feature is computed. Maybe the semantics are the same, but the new implementation is slower. So you want to test to make sure that, in this case, if the time required to compute a feature goes from 1 millisecond to 20, maybe our credit card, an online credit card fraud prediction service is no longer usable by the client. They need the response within 10 milliseconds or 5 milliseconds. You should also unit test code that creates input features, which is pretty obvious. And then when you've trained models, you can do a bunch of tests on models. So you can test every model specification should undergo code review. That's a reasonable, maybe not automated test, but something that can help a lot. You can test the relationship between some sort of offline proxy metric. So often we don't know the outcomes of all predictions, but we can have some proxy for it. And then we may have a model has a KPI, so a key performance indicator, so the actual impact metrics of the model, and we may have some proxy for that. So maybe we're trying to increase revenue, but to do that we're trying to increase engagement on a platform. So we can't maybe necessarily measure one, and we'd like to use the other as a proxy metric for the other. When you're training and experimenting, you want to do things like test the effects of individual hyperparameter tunings, test what happens when a model becomes stale, have a simpler model as a baseline, and test your model to make sure it performs better than your baseline. And often you have models where they perform incredibly well 95% of the time, but poorer than the baseline 5% of the time. And in that case, it might even be better to use the baseline. And then finally, test the model quality and test against bias. So you want to make sure that your model performs well, not just over the average of all your users, but over key user groups that might potentially be biased against. And you can use something called evaluation sets to identify those sets that you want to test for bias against. So it's not just features and models. You also have to deploy your models. So you need to infrastructure, and you need to monitor models. So they identified more tests related to infrastructure. So you can have integration tests for our different pipelines, the feature, training, and inference pipelines. We want to make sure that models should be reproducible. Test the quality of the model before serving it. When we deploy a model, we'll want to make sure that we can do A/B tests. We can have a canary process to make sure the model works okay before we actually deploy it for serving. And then also be able to test that we can roll back our model safely, because if we upgrade a model and there's a problem, we want to make sure that rollback works. When models are deployed, we want to make sure that the data coming in, the new data that we're going to make predictions on, that its quality is good, and that any invariance in that data hold, both for training and serving. We want to test that if we've got on-demand features, or we saw already the model-specific transformation functions, that they're consistently computed between training and serving. Obviously, you need to check a model if a model becomes stale over time. If you get your model training doesn't work because you get NANs or infinities, and that could happen in training or even in serving, we want to test for those cases, and you can also test for robust input, like so if there's missing values, you can often train a model to handle missing values. And then I mentioned already you can test for regression. So if you've retrained a model but the model is now slower, you want to be able to identify that before potentially it goes into production. So these are all the tests, and they kind of cover the features, the models, and the infrastructure. And I'm going to go through a bunch of them, and this is the kind of the ML system end to end that I'm going to go around. So let's assume this model of an operational machine learning system consists of all the pipelines we've talked about. We have a feature pipeline which takes data from a data warehouse. It may also take prediction logs to create new features from serving. We then have the feature store, which provides data for training and also provides data, inference data for serving, so via the online and offline APIs. We have the model-specific transformations that are applied on the untransformed feature values in the feature store to create the training data, but also to create the inference data. We have our model registry down here, and then we have the actual services, the prediction services that are going to use the model to make predictions with. So this is our model for a machine learning system, and let's look at where we can apply tests at the different stages. So in orange we can see the tests highlighted, and you can see there's a lot, and this is kind of reflective of many of the tests that Sculley identified in his seminal paper. So if we start at unit tests, we can see that we can have unit tests for features, so that's this one here, and we can have unit tests as well for the model specific transformation functions, and also for on-demand feature computations as well. We can test these feature pipelines end to end with integration tests. The data that's written in the feature pipelines, we're going to look at Great Expectations as a framework for validating that data. You can also validate the data asynchronously, so you could write the data to your feature store and then asynchronously validate it. A little bit more risky because you may have garbage into your feature store that may end up being used that you don't want to use. But it's one way at least of, it's a good way of getting started. You can have some raw data that you can asynchronously create a profile from and use that profile to validate new data that comes in. So when you train models, you should also test your model. So we'll need to have a model testing phase. When we want to deploy a model for serving, we should have A/B tests so that we don't just deploy the model and maybe it performs very poorly. We gradually roll out the model to production. And then finally, when the model is being served, we should monitor not just the predictions being made, but also the input feature values so that we can see any anomalies that appear. So we're going to go through all of these different steps now. And we're going to look at them with a few technologies. So they are very abstract. So let's get a bit more concrete. How can I implement these in my system? So you can use Pytest, which is a unit test framework for Python, for doing what we call offline tests. So example of offline tests, I've given you some already. So computing feature logic, running feature pipelines, trying out our model-specific transformation tests, and also the on-demand feature tests, and then even testing models for bias we can run with Pytest. So we can have a trained model, and then we can use some sample data or some test data to make sure that the model isn't biased against that test data. Now there's also online tests. So online tests run both in production. You can also run them in training or in offline when you're testing, but typically we can think of them as being validation steps in a production system. So for example, when feature pipelines being written, we can perform runtime data validation. That means we validate the data before it's written to the feature store. We can also validate it later with asynchronous data validation. And then when our models are being served, we can do gradual rollouts with A/B testing, and we can also monitor the features and the predictions. And in this case, we can use Kserve for the A/B testing, and Hopsworks can help us. We can store our prediction logs and even our outcomes in Hopsworks, and we looked at how we did that in feature groups in the first lab. And from there, then we can monitor the predictions and the features for any anomalies that may arise. Okay, let's get started with unit tests. So unit tests are primarily used with Pytest in Python. It's a very popular framework. Here's a very simple example of a unit test. Here we have a function called inc, and it increments an input parameter x. So we assume an int has arrived as a parameter to the inc function, and we increment it with 1. So if we're testing this function, we can have a function here called test answer, which will test that at some input, when we call increment on it, will give us the correct answer. So in this case, it's giving a test input of the value 3, and we expect that if we increment 3, we'll get the answer 4. Now, often a kind of a more thorough test would check for edge cases that could be problematic. So maybe incrementing a negative number should work. Maybe a 0 value should work. It shouldn't cause a problem, but this is good enough for the general purpose of understanding what it means to write a unit test. So a unit test is we have a function and then we run another function to test that function. So we've already mentioned unit tests for feature logic and on-demand features and model-specific transformation functions, but these unit tests in Pytest can be run very easily by Jenkins. So if you make some new code changes for any of these function definitions that are computing your features or transformations, when you push that code to a GitHub repo, Jenkins can run all of these tests. It can run all the unit tests to make sure that the new code that you've changed hasn't broken any expectations that are written into the unit tests. So increment should continue working as before, even if you change the implementation of it. So in order to do that, the starting point really is that if we want to be able to test our features, and we need to refactor our notebooks. And often our notebooks look like this. So we can see here that we have a function called compute features. It takes in a data frame and returns a data frame. And where do we get the data frame from? Well, we get it from some external system, and then we call compute features. On the data frame, we get back a data frame, and then we can write that to the feature store. And you're really happy. This is a great feature pipeline, wonderful. But the problem is that the feature logic in this function, compute features, it doesn't contain any independently testable features. So I can test compute features as a function. So we can go ahead and say, to a new person who starts joining. So some girls start joining, and we say, okay, the first thing I want you to do is write unit tests for our features. And she comes along and says, well, I can write a unit test for compute features here, but there's a lot of different features being computed in here. There's one for holidays, one for average 3-week spend, acquisition costs, spend shift 3 weeks, special features, spend B. They're all in the same function. So the easiest way to handle this problem is we refactor our features into individual functions. If we take the average 3-week spend computed on the previous slide, we can see that we define it as a function now. So it takes in as a column the value spend, and then it computes this rolling 3-week average over the series. So another feature that we have here is spend per signup. So this is going to take in the amount of money spent, the number of signups, and it's going to divide the number of the spend by the number of signups. So we can test this function here, the spend per signup, by defining a unit test. And here we define one called test spend per signup. It takes in 3 different columns. You can see here we have the spends, the signups, and then we have the expected spend per signup. So we pass in spends of 20, we have signups 5, so we'll expect that the spend per signup will be on average 4, so 20 divided by 4. And then we have 40 and 4, and we expect an output of 10. So when we call test spend per signup, this get spends will be our data frame with these 3 different columns, and we've got our 2 rows. What we want to do is then compute the spend per signup using the spends and signup columns that we supplied as input values, and we're going to get the answer in a res column. So this result column should be the same as the values that we supplied here in spend per signup. So it should be the same as 10 and 4. Okay, so it's going to call this our original feature computation function, spend per signup, with the input values 20 and 5, and then 40 and 4, and it should give us back answers 4 and 10. And if they're correct, then this assertion will succeed and our unit test will pass. Now, if somebody changed, for example, how this feature is computed, maybe they want to compute some other type of average spend per signup, then the unit test might fail, because downstream clients are dependent on, maybe dependent that this is the expected behavior of the function spend per signup. And if you change it, the unit test should warn you that you've changed the semantics of this spend per signup feature, and it may break downstream clients. So how do we, now we've defined a unit test, and it looked like it was all together, right? We have, here's our functions and here's our unit test, but we typically don't have them all together. We typically put them in a separate directory. So if we have a directory where we define our features, so maybe we've got our features that are used in the feature engineering pipeline. So for example, you might have a backfill and a production one. You may have on-demand features, custom transformations. You can put them all in separate modules or even in the same module. But you should have then a separate test directory where you put your tests. So for example, we can have a test for all of the modules in the features directory in a folder called, or directory called test_features. So we can create that file and then put our unit test in there. The same we can do for pipelines. So we have our feature pipelines and maybe and our training pipelines and batch pipelines in a pipelines directory. We can have a separate test pipelines directory where we can include all of our integration tests and then run them with Pytest. So this is a reasonably common directory structure that you have. So if we take the features, this is our module. This is our package where we include the feature modules, and then obviously pipelines are the Python programs runs pipelines, and then the unit tests will go in the last two directories that are prefixed with test_. Let's have a look at the integration test for a feature pipeline. And when I say in a CI/CD setup, we mean in the case that it's continuous integration, that when you, for example, push new code, you could kick off this pipeline integration test. And maybe if you wanted to change the available data, you could also kick it off. But let's assume that then deployment in this case means really just writing the features to the feature store. So when we've computed the features, we'll need to also write them to a development feature store if I'm in development, or a staging feature store when I'm in staging environment, or production in production. Now, this means that you do have to have your program connected to a feature store. The feature store does need to exist. We're not going to mock the feature store. Often you can use unit tests and mock out things. But an integration test is just making sure that the system works end to end. So typically what you would do to make this easier, maybe you, instead of connecting to a production system to read the data from, you can often take some subsample data. So typical data that would be used to create features with. Maybe it's it's a snapshot of data from your production system, and maybe you need to anonymize it or something. But you can check that data even into Git. Make sure that you're able to do that from an ethical, legal way. But it's often convenient to have a small subset of data committed to Git with your feature pipeline. That means that you can use Pytest and Jenkins to check out the code, but also this subsample data. And then all your program needs to be able to do is connect to the feature store with an API token to be able to write the features there. So we can then run this feature pipeline test end to end, but instead of connecting up the source data, we're effectively mocking it by connecting it to some subsample data that we store in the GitHub repo. Now let's move on a little bit to another challenge that you may face, which is that you're adding features and you're putting them in separate functions and you're happy with it, but it's becoming a challenge to add tens or hundreds or even thousands of features. So Stitch Fix developed a framework called Hamilton to address some of these challenges of adding potentially thousands of columns in a feature group or a training data set. And one of the things that they saw quite often was that many columns are computed from other columns. So if, for example, we have a year and a week as a column, we might be able to compute the holiday, whether it's a holiday or not, based on those existing columns. And in the earlier example that we had about the average 3-week spend, acquisition cost and spend and so on, they spend shift every 3 weeks, they're all computed using the spend column. And in that example, we even had another feature which was computed from the acquisition cost, which is in turn computed from the spend column. So what you have is effectively a directed acyclic graph of feature computations. This is quite a common scenario to encounter. So in this case, we have some core data, which is our spend. If we go back and think of our data warehousing lecture in lecture number 2, we often talked about facts and dimensions, and you can think of it spend as being a fact at some level. This was an amount of money spent, and then the dimensions are the features that we're computing off that original fact. So in this case, we're computing acquisition cost, spend shift 3 weeks and average 3 week spend from the spend features. And then the spend underscore B we can compute from the acquisition cost. So obviously in larger systems, these direct acyclic graphs can be quite large. Now, in many cases, people think, oh, when they hear direct acyclic graph, they think of frameworks like Airflow, Daxter, but these are really, those frameworks are orchestration frameworks. They're for running DAGs of jobs, right? So complete jobs, right? Now, in this case, we're just talking about computing individual features from other features. So it's going to be the same Python program. It's still a direct acyclic graph, but it's within a program. And Hamilton is a way of making it easier for you to build a DAG of these feature definitions, enabling it to scale to manage hundreds or thousands of features. And I'll give you an idea of one example of why that is. So imagine you have lots and lots of features in your system, and Stitch Fix say they have some systems with thousands of features in a single data frame, where you're going to have many data scientists working on that code. So what you can do is you can say, okay, new data scientist comes in, who's going to compute 2 new features, average 3 week spend and spend per sign up. They can go and write the code in their own Python module. They can define a file called my_functions.py. They can compute the features, and they're going to use spend column to compute them, or the spend and signups columns, and then they can define this and test this independently. So many different data scientists can work independently on this same huge data frame that's going to be used to train a lot of models. How do we put our functions together to build this very large pandas data frame that we're going to use to train our models with? Well, with Hamilton, we have a driver that you need to define, and the driver will execute the code to build the data frame as a directed acyclic graph of functions. So it's going to compute these features or functions in a particular order defined by this directed acyclic graph, and we need to tell Hamilton in this case what are the columns that we're going to compute, and we'll do that, as we can see here, with our initial columns. We can say, okay, let's define the initial columns. We've got signups, spend, and we pass them into the driver, and then we also specify the functions that we're going to compute over those columns. So we'll have our initial data frame with our initial data. There's going to be some derived features computed from those columns, and we tell Hamilton in this case, here are the columns and in our input data frame, and here are the functions that are going to be executed over those columns. And Hamilton will figure out which ones get executed first and which are the dependent ones which are executed after it. And we also then can see that we have our output. So we define also the output, and we can retrieve the output by calling dr.execute on the output columns, and we'll receive those back as a data frame. And then this is the final data frame we'll have with our features that we can use for training models, but also for batch scoring if you use it for that. Okay, let's move on, and we'll look now at what we call data validation. So we want to ensure that the data we're using to train our models with, the features, is correct. If we have garbage in our feature store, we'll probably get garbage out of our feature store. So how do we ensure that the data that we write into the feature store is valid and there's no anomalies or missing data? Well, we're going to look at a framework called Great Expectations. It's an open source library. It works very well with pandas. It's Python. It also works in Spark. And what Great Expectations enables you to do in your feature pipelines is that you can add some declarative statements to validate your data before it's written into the feature store. So you might, for example, say, well, I've got a categorical variable. I know there's 5 different categories. If data comes in from an unknown category, maybe that's bad because I don't expect data from an unknown category to arrive. I can trigger an error. Or maybe I'll let that data in and I'll just print a warning or something like that to warn people that a new category has arrived. So it's a very flexible framework allowing you to handle these expectations. An expectation basically means I expect data to look like this, or to this integer to fall in this range. And if it doesn't, then you're flexible in how you handle that. So what HopsWorks gives you on top of Great Expectations is it's integrated into the platform. So Great Expectations will produce reports. There's these validation reports for every time we write to the feature group with a feature pipeline. HopsWorks will give you a validation report for it, which is great. It also manages the expectation suite by attaching it declaratively to the feature group. And that means your feature pipeline doesn't need to have all the complex code when it's writing to the feature store, defining these expectations. We can define them once, and then when we're writing to the feature group with a data frame, Hopsworks will execute that code transparently for us. And this keeps our clients nice and minimal. And the expectations are associated with the feature group, so the expectations will be executed as normal, but you won't have to have all that code littered into the standard feature pipeline. Okay, let's look at some of the rules. I mentioned a couple of them already. Python is a dynamically typed language, so you might want to add type checks, for example, to your code. Let's jump back here. So we have type checks. We might want a value range. So we want to make sure that for example, a distance should not be negative. The age for a human shouldn't be over 150 maybe. If there's missing values for a required feature, that's probably not good. We might want to have an error. If we have an unknown value for a categorical feature, so set membership is broken, or even at the table level, we can define expectations, checking all of the expected feature names are present in a table, for example. So these are the kind of rules you can define. The rules are defined as what we call expectations, and we can see an example of one here. This one here, you can see if we look at it, it says the expectation type, and there's a built-in set of expectation types in Great Expectations. It's growing all the time. This one says expect the column min to be between two values. We can see that the minimum value, which is the age at transaction. So if we're looking at our credit card transaction example, we expect the minimum value to be between 18 and 130 for all of the data that's going to be written in the data frame that we're writing to our feature group. Now, this rule or expectation will be validated against the data frame that we're writing in. This is our pandas data frame here. And it's going to be validated against the column called age at transaction. The report or result of that validation operation is a JSON. So we have a JSON here saying success was false because we observed a value that was 17.73, and the offset at which we observed it was an element count 106,020. So we had a problem because that's below the minimum value of 18 specified over here. And that result, you can get it back as a JSON if you want from Hopsworks, but often it's easier just to read it from the user interface. So in the user interface, you'll be able to see a nice validation report. Now here we can see it in a little bit more detail, and we can see an example of Great Expectations here. So what we can, if we go through this code, we'll be able to see how Great Expectations can work with the feature store. So firstly, we need to import Great Expectations, the library, and we need an expectation suite, which will contain many expectations. So when we define expectations, we put them in an expectation suite, and then we attach that expectation suite to a feature group. You may need to configure expectation as well. So what Great Expectations does is it wraps the pandas library. You can take a pandas data frame like this one, agsdf, and you can just call it GE or Great Expectations from pandas, and now you'll have effectively a Great Expectations object that looks just like your pandas data frame. So with that, you can do things like profile the data to generate an expectation suite. So this is great. You can asynchronously, if you have some pandas data frame, you can say, okay, asynchronously, give me the data, I'll generate, assume this is what data should look like for this feature group. I can read all the data from the feature group. I can generate an expectation suite from it by profiling it, as we're doing here. This is using the basic suite builder profiler. There are a couple of other ones. And then with that expectation suite, we can basically attach it to the feature group and say, hey, all data that comes into this feature group should look like it. That's one example of what you could do with that expectation suite. But what you can also do is you can say, well, I'm going to add some more rules to it. So for here, I'm going to add expect column values to be increasing for the date time column. That's maybe a reasonable assumption if you assume a monatomic column called date time should always give you increasing date time stamps. And we add that expectation here, this validation results, we're adding it to that suite. So we got the suite from profiling the data. We've added an extra rule that we know about. We can add another rule here. And this one is saying I expect column values to be in this set. And for the fraud label, it's going to be either true or false. We don't want any other labels in there. And then what we can do is, we can say, okay, this agsdf that we had originally and this expectation suite, give it back to us, and we can then actually run validate on it, and that will give us the validation result that we've saw before. So this is just pure great expectations code with pandas. There's no hopsworks involved here, and that's kind of how you can use the library. Now, you can also, of course, as I mentioned, attach that expectation suite to your feature group so that when you write the data, it'll get validated transparently for you. Now, if we put all of what we've looked at so far, unit testing for features, pipeline tests, and great expectation rules or data validation rules, all of those together make up a set of tests that we make sure that the features and the data that we're writing to the feature store has correct feature logic, that it works end to end, and that the data is being validated. Now, one of the challenges with great expectations rules is you can write them, but they run in production. So if you have a bug in your great expectation rule and it's running in production, it could be problematic. So you want to test your rules. And you can test your rules basically by getting a subsample of the data that your feature pipeline that's representative of the data that your feature pipeline would process when it's creating the features. Get a subsample of that and put it in your source code repo. So put it in GitHub, a CSV file, a Parquet file, and then when you're running your tests, what you can actually do in your pipeline test is you can read up that data, compute the features, and run the great expectations rules or expectations before the data is written to the feature store. And that way, you're testing these expectations to make sure they work as you would expect them to work, and there's no errors in them. Then with confidence, you can push them maybe into a staging feature store and finally into a production feature store. The way you typically can set up this CI/CD pipeline is that if you're testing on your laptop or in a virtual machine on the cloud, typically you run Pytest manually. So when you've written your feature pipeline, you might write some feature logic tests in Pytest. You might have an integration test or a pipeline test that will test it end to end on this subsample data, and then you've added your great expectations rules, and you make sure that they work as expected, and you'll connect this to a development feature store. So you might have a project in Hopsworks which is just called development, and then your feature groups end up in that particular project. And when you're happy with that, then if you have a CI/CD pipeline set up, you can push your code that you've written here for your feature pipeline to something like GitHub, and then Jenkins can actually check out that code along with the subsample data here. So check out our code here, the subsample data, and then it can run your test with Pytest. Obviously, you'll need to have environment variables that point to this staging feature store, and also you'll need the API key for Hopsworks, but you can configure those environment variables in Jenkins, and then Jenkins will be able to run the unit test for the features, the pipeline tests for end-to-end, which will also run your great expectations tests as well. So that way you can have great CI/CD setups for validating the features before you push anything into production. So if you assume now that we have a great setup for testing our features, using Pytest to drive most of these tests, then we can train models with them with confidence, and that's brilliant, right? But the models themselves, we need to also validate and test to make sure we can build our intelligent applications against them. So the training pipelines that are used to create the models, we can test those, and even the models then that we've created, we'd like to validate those models as well before we deploy them into production. So let's have a look at some of the things we need to do here. So firstly, if you're training lots of models, and sometimes you may be tuning hyperparameters and running many parallel experiments to make sure you get the best model, the most accurate, the highest performance model, the most robust model. So typically people use experiment management platforms, weights and biases, MLflow to manage all that. You can save the hyperparameters and training data along with your model so that this model was trained on this training data, but these were the hyperparameters used to train that particular model. So that could also be a snapshot of the training pipeline program. If the hyperparameters embedded in it, that will work for you too. If you're going to deploy a model to production, you really only should deploy a model that outperforms the existing model. So it needs to pass all our tests, but then ultimately there's no point in deploying the model if based on your metrics for your model, if it's not better than what's there, you typically wouldn't redeploy it. Now, it could be the case that the current model is being flagged as being stale, so you need to redeploy. That's fine. But in the general case, if your new model is not better than the old one, why should you deploy it? Now, so the assumption that they're both trained on the same train data set is probably not going to be true if you're working with time series data, for example, because new data arrives the whole time. Your model will get stale over time. And even if the accuracy on the previous trained data set is higher than your model trained on the most recent trained data set, they're not being trained on the same trained data set. You can't say that the older model is better, right? Because that might not be true. There's no point deploying a model if it's not, as far as you can, with your best effort, you've ensured that it's free from bias and that it's trained on ethical data. So that's your responsibility. If we don't have legislation to ensure this doesn't happen, it's your job as a data scientist to make sure that you make sure that this happens. Okay, so let's have a look at the kind of things that can happen. We have our training pipeline, which takes features and it produces models in the model registry. That's pretty straightforward. That's what we have here, but we can break it down into many sections. So you can have, hyperparameter exploration and parallel experiments for that as an additional step here if you'd like. Feature selection could also be an additional step at the beginning. But at some level, the training pipeline has to be triggered or kicked off. And that can be done manually. It can be done on a schedule. It could be when new data arrives at a feature group. There's many reasons why you would train a new model. So after you've trained your model, you need to evaluate your model. And by evaluate our model, we mean really to evaluate the performance of the model. So it might be the accuracy of a classification model. It might be the root mean squared error of a regression model. But note roughly, is this model going to be good enough for the task we're training it for? If the model is potentially good enough, we're still not sure we're going to deploy it because maybe the model has bias in it. So if we have bias tests, then the bias test might take, for example, a subsample of the test data. Maybe we've got test data for consumers and we're going to subsample it by, or break it down by gender, or break it down by ethnicity. And then we can evaluate the model on those subsets. We can again perform our performance test, but this time on these evaluation sets is what we call them. So an evaluation set is a subset of your test set where you're looking at some subgroup that you'd like to test for bias against. And as I mentioned, maybe it's particular speakers of a language, or maybe it's ethnicity, or it's gender, or it's where you live. But you want to be able to extract that data from the feature stores. You might have to filter, for example, when we create trained data sets in Hopsworks, we can say filter where gender equals X, filter where first language is equal to Y. And then you can get that test data, evaluate the performance of your model against that one, and compare it with the performance against all the other evaluation sets. And then if there's not too much deviation between them and they're all as expected, then maybe you can go ahead and deploy your model to production. So evaluating your model and your testing your training pipelines involves evaluating the metrics of your model for acceptable performance. I mentioned already it might be accuracy and classification, for example. But you also want to do post-training tests on the model's learned behavior. I mentioned that you want to test for bias, for example. But you might also want to do tests that, for example, does your model do crazy ass things, right? So maybe the model, if it's giving recommendations and gives will it give really, unexpected recommendations that cause people to change their perception of the system. So you want to avoid that. So you can do those kind of tests as well. You can also, of course, compare the performance of your model with previous models, and you have a stateful model registry that helps you to do that. You go to the model registry, it has some metadata about the performance of the existing model, and you can compare your new one with the old one. And then you'd like to also do the same type of integration test we talked about for the feature pipeline. We'd like to do an end-to-end test of the training pipeline. We want to make sure that it's able to select the features from the feature store, train the model, do the evaluation of the model, and then publish that model or deploy it to the model registry, and even deploy it to serving potentially if you want to also do not just CI or continuous integration, but continuous deployment as well. Now, evaluating the performance of a model, I said that, of course, you can use accuracy for classification and so on. Um, it's a huge area by itself. So the basic commonality you will have when you're evaluating the performance of your model is you'll have some sort of evaluation report. Now, if it's a simple one such as accuracy on a classifier, that's fine. But you may also have, in this case, you can see we have a slightly different evaluation metric, which is the area under the curve of a receiver operating characteristic. So ROC curves, as we call them, and the AUC of ROC is it's this little area up here. We can see if we just mark it in here, this area under here, where we're trying to see this is the area where the model's not performing as well as it could, and the larger that area is, the worse your performance is. So the baseline here, where you have a random model predicting randomly, is this line going through the middle. So if you're above the line, you're obviously good, but the smaller this area is up here in the corner, the better your model is performing for both true positives and for it's minimizing a number of false positives. So you can see here the general performance of some models is as you increase the accuracy, or sorry, in this case, the true positive rate, and you can see it's approaching 1 up here, but it's also creating a lot of false positives. That means it's predicting everything is positive, which means the true positives aren't missed. It also means that you're predicting things that are positive that are not positive. So you obviously don't want to predict false positives, and you do want to predict true positives. So if you're up right here in the corner, then you have a perfect model, but that's rarely the case. So precision recall is the kind of basis for these ROC curves, because you can also have F1 scores, of course, which show you the performance of your model for both precision and recall. And there are other types of evaluations that might be of interest to you. For example, you might care about if you're training a deep learning model and you add more and more layers, maybe the inference of the time it takes to make a prediction increases beyond what is acceptable for your application. So sometimes operational statistics or measurements are important for your model. Other tests you can do is, after you've trained, I mentioned already, you can just have some pre-canned tests to make sure your model has some sane behaviors. So expected behaviors could be invariance in the model, and you could, for example, know that for the Titanic survival data set. So the Titanic data set's a well-known data set for you train on features such as, is it a man or a woman, are they first class, second class, third class passenger, and we know that more women survived the Titanic than men, so that's the target. We're trying to predict if someone survived or not. And if you train a model that predicts more men survived than women, then that model is probably incorrect. So you can encode those as tests to make sure that the model is sane. And the bias tests we talked about already. And I just point out that evaluation sets are a really useful tool for doing bias tests. So you should know in advance for your data where the potential for bias could exist, identify those evaluation sets or those groups of individuals, and then extract them from your test set. Or not from your training set or validation set, but from your test set, and then score the model against them. So you will need enough data in your test set in order to not suffer from too small an amount of data, so that your bias tests are underpowered and you maybe have got too high variance because they're underpowered. So this is kind of how you can generate or build these evaluation sets in HopsWorks. You can basically apply a filter when you create training data. So when you create your training data, you can have a train set and a test set, and then you can apply a filter and say, hey, I only want to filter on the test set, and we'll take a region. So I'm going to test for bias of whether we're biased against users in EMEA, North America, or Asia. So we'll end up with 3 different subsets of our test sets, and then we can score the model against all of those 3 test sets, evaluate the model for its performance. And we're looking, of course, for statistically significant differences in the performance of the model against the 3 different groups of users in this case. Now, we have the same challenge, of course, for training pipelines as we had for feature pipelines. We'd like to automate the testing of these pipelines and the testing of the models as well. So you can do that again with Pytest and Jenkins. You can, when you're developing, have your own branch of the code. You can define all of these different types of tests. The model tests we looked at, bias, behavior, and performance tests. You can also, let's go back here. Here we can also have an end-to-end test that trains a model with some training data. It can potentially get that from the feature store, or it can exist already. And the same with the valuation sets. We can create them from the feature store. Typically they mightn't be committed with your Git code, so you would just have a reference to them in your code. And then if you also want to make sure that your training pipeline works end to end and it deploys models, you can even have it deploy not just the model to model registry, but even deploy the model also to a serving environment, and then test that you can make predictions against that model as expected. And then this pipeline is really just code, and the external dependencies are the HopsWorks API key to point to the feature store, and then we have the training and evaluation sets here. So when you push this then to say a staging environment, you push your code to maybe some branch in GitHub, or create a PR to a particular branch in GitHub. And then Jenkins can check out your code. It'll check out this complete training pipeline, and Jenkins needs to be set up again with access to that training data. So maybe you wouldn't have this data checked into Git. Probably doesn't make sense to do so, but in some cases, if it's small data, you would. But then Jenkins needs to be able to point this code to it. So you have an environment variable, or even in your code, you might be able to give a relative path name to the training data and the evaluation set, so that they can be used and just run as is. And then the model will be then finally deployed to a model registry, and potentially even deployed to serving if that's part of your tests. Okay, so imagine we're confident that the models that we've trained, they look good, they pass all the tests, they pass the different bias tests and performance tests. And what we'd like to do is we'd like to test the performance of this model in a live operational machine learning system. So we're going to deploy it to model serving infrastructure. And the HopsWorks case, we can see that HopsWorks model serving is based on a platform called Kserve. Kserve is an open source model serving framework developed as part of the Kubeflow project, but now it's a standalone project. And it's used widely by many companies such as Bloomberg and IBM. And what Kserve gives you is the ability to take a model from your model registry and deploy that model, and then you can deploy an A/B test. You can say, for example, I have a model here. This model is called model-A1, and what I'd like to do is I'd like to deploy model A2, but I'm not really sure if it's going to work really well. So what I'd like to do is keep model 1 as it is. All of the traffic that's coming in, all the requests to make predictions, go to model 1. So 100% of the traffic goes to model 1. We call that the blue model. Now the green model is the new model I want to try out. So when you deploy it from your API, from your Python code, HopsWorks will deploy that model, and it will tell Kserve, hey, this is a blue-green rollout. I'm going to give 10% of the traffic, and it's going to be mirrored. So the 100% keeps going to the blue model, but 10% gets sent here to the green model, because we're going to just see how this model performs. So in this case, the model can log the prediction results and log any other outputs that it has, maybe some pre-processing as the request comes in, or going to get featured in the feature store. And then you can inspect those. So you can basically just then see how the model's performing, make sure there's no obvious errors. And if everything's going great, you can then increase this 10%. And finally, you can just replace the model with the new one when you're happy that it can handle, both the performance requirements, but also that it's correct. Now, if we have all of this infrastructure in place, in fact, there is a kind of a vision of MLOps. It's a vision I have in my head of what is great MLOps. Great MLOps is having a big red button. So if you're an operations person and deploying a model is pressing the green button, which most people think is fantastic, I can upgrade. So here we can see we've got a nice big green button. And what the green button gives me is the ability to say, hey, I want to deploy V2 of the fraud model. When I press the green button, I get V2 of the fraud model. But remember, the fraud model that's running online here, it'll need access potentially to new feature groups, because maybe it's got new features that aren't used in the previous version of the model. So in this case, it's connected to this transaction V2 feature group. It's going to get its live features from there. But the old version of the model over here, it took its transactions from V1. that version of the feature group. So we need to do this synchronously. We need to synchronize the upgrading of both features, feature groups, and models. Now that's not too hard because in HopsWorks you can add a transactions version feature 2, v2, sorry, and you can have the existing v1, and the feature pipelines for both of them can run in parallel. So you're going to write them to v1, write them to v2, and that's no problem. So you deploy version 2 of the model, and it'll hook up to v2 of the transactions, which is already there, and you're happy with everything. And then suddenly, whoa, the model v2 starts performing poorly. So what do? Well, I press the big red button. Simple as that. So the big red button, the rollback button, should just roll back my model to v1, and then the clients who are using the fraud deployment, they don't know if it's v1 or v2. They're just making a request on the model, but they'll get routed to v1 deployment, not to v2. And then v1 is already connected to its feature groups to get its online features, and then hopefully then there's no problem for the clients. They're transparently redirected to the working version of the model, and then you can go back and fix the problems in v2 before you go back and press the green button to upgrade again. So if you have models being deployed like we talked about in Kserve, we'd like to monitor them. Now the bigger picture for monitoring of models is that there's a lot of data being generated when models make predictions. We call them feature logs and prediction logs. You're basically, models produce a prediction, and to produce a prediction they have some input feature values. So you should save this. In general, this is incredibly valuable data. It's valuable for debugging your models, being able to say, hey, there was a bad prediction. Okay, let's have a look at what did the prediction look like? What were the input feature values? In the debugging case, what you'll think as well is that it's actually very important also that you don't log the transformed feature values. So if, for example, we have the amount of money spent on a credit card and we normalize it, so we normalize it within a range of 0 and 1, we won't see the actual spend on the credit card. We'll see the normalized version of it. That's not going to be very useful for debugging. It's actually not also going to be that useful for monitoring either, because it becomes harder to find outliers in that case, because you've normalized them. So often we'll want to have the untransformed feature values, and in HopsWorks you will store the untransformed feature values in the feature store, and they're retrieved by the models, or you create training data from them. And in this case, if we're going to do batch scoring, we can use the same feature selection code, select the features that we would train the model with, but when we get the features, we can log those before we transform them and do batch scoring. And similarly, you can do the same for online. You can log the untransformed feature values along with the prediction that's produced by our model, and that will be much more valuable than having the transform feature and prediction logs. So the other great thing, apart from just debugging and observability, is potentially you have new training data in these predictions that were made. So if, for example, my prediction service is a recommendation system, well, you clicked on some item. I recommended 5 items to you, and you clicked on one of them. I predicted that you clicked on one as well. So I now have potentially 5 new training points, one for the one you clicked on, and then the other 4 for the ones you didn't click on. So the one you clicked on gets a 1, and the other 4 get a 0. So that outcome can arrive, and the outcome might arrive not via this system here. Maybe you've got Kafka here. So when you clicked on one of the items that was recommended, that event got sent in here, and it contained the item numbers, so 1 to 5 in here, and then you have a 1 for the one that you actually clicked on and 0 for the others. And with that data, we can feed it again back over into the feature store and join it up with the input feature values. So the features that we use to help make the recommendation by the model, and also then the prediction made by the model. And then together we'll be able to create new training data, and with new training data we'll get better models. That's great. The more clean training data we have, we'll get better models, and with better models we should be able to attract more users to our system. And if we have more users, we'll be generating more data, more logs, and with more logs we can generate better models, getting more users. And this is what we call the data for AI flywheel. And what that means is that it's a system that gets better and better by itself, because as more people use it, you get more data, and as we know, machine learning models perform better with more clean data, and better models should attract more users. So I mentioned already that the logs of features and predictions can be used for debugging and creating new training data. But the other thing they can be used for is just purely monitoring the features for example, anomalous feature values, and the same for predictions, and the same also for performance. You want to monitor how long it's taking, for example, to make that prediction on that model. You know, is this model very large and the predictions are taking too long or not? And I mentioned already that you should also log the untransformed feature values because they have a lot more information in them. You can, in some libraries like scikit-learn, you can, if you have the transformer, you can also call reverse transform on it. So you can have the output feature or label, call reverse transform it with the transformer object, and you'll get back the original value, and that's okay too. But it's easier to have a kind of generic mechanism that just works, and you don't have to then ensure that the programmer does a reverse transform, and the programmer might forget to perform the reverse transform, for example. Okay, so monitoring of features and labels and predictions and outcomes is really important, because this helps you identify when new data coming in is problematic, maybe when models are becoming stale, and just when models are performing poorly. So one way in which you can help monitor machine learning systems is to monitor individual distributions of features or predictions or outcomes for something called drift. So for example, if I create some training data, and we'll have a look here at this is our training data here, we'll know that training data has features X, so uppercase X, and you also have the labels or outcomes lowercase y. So over those input features, we can define the distribution of the values. If they're numerical features, for example, maybe they follow a normal distribution or Gaussian distribution. Okay, great. Or maybe they don't. Maybe they follow an exponential distribution. Fine. And the same for labels. Maybe they're uniformly at random distributed in that way. So when we train a model, the model will have these assumptions that the input features come from this distribution, so that we're not getting out of distribution input features and we're supposed to predict with them, because the model never saw those out of distribution features before. We don't know if it'll perform well. So we'd like to maybe get warned if new values come in that are out of that distribution. In that case, the new data that's coming in, the new features that we're going to score the model on, we call that the inference features here. So this is the inference data coming in that we're going to make predictions with. And the inference features are defined under the distribution Q of X, whereas the training features were defined under the distribution P of X. Now, if Q of X is significantly different from P of X, we can have what we call feature drift. Now, in this case, because it's inference data coming in, I'm using the term operational feature drift. You could use the term inference feature drift as well, but it's operational. It's happening in the operational system. It's not happening beforehand when we're creating training data. This is when we're getting new features in that we want to make predictions with. Now, this is to differentiate that from feature pipeline drift, and the feature pipeline is used to write the features to a feature group. So in the feature group's case, we have the data that exists in the feature group, and we have the labels and we have the features. So P of X are the existing features in a feature group. When we're going to write new data to a feature group, what we might want to do is see if the new data has drifted compared to the existing data. So the new features Q of X, we can compare their distribution of their values with the existing features P of X in the feature group. And if they're significantly different, statistically significantly different, we can potentially flag for drift and then reject that write. Or we could just allow the write and then tell some administrator, hey, I'm warning you, there seems to be drift here for these features. Do you want to back out that data? So reverse the commit to the feature group, or would you just leave it in there? Now, other places that we can have drift are in the labels. So the labels, as we know, these are our labels in training, P of Y. And if we imagine we have a single label, maybe it's fraud for credit card detection, and we look at the distribution of fraud cases. So maybe we've got like 0.005% of all credit card transactions are fraud. we can look at the distribution of that, the fraud labels in the positive fraud labels in the label group. Now, if in a real world we have predictions, so in this case Q of y hat, so the predictions made by the model, that's these predictions here, and we look at the distribution of the predictions, and if they're significantly statistically different from what we saw in training, we might want to warn. We say, okay, it seems to be that the predictions being made are different. You had 0.005% when you were training, but now it's gone to like 0.1%. This is a huge difference. You're now warned. You want to do something about it. In many systems, the outcomes of a prediction can come quite quickly. So in a recommender system, if I get recommended, let's say 5 items, and I click on one of them, and this is what TikTok do, for example, then within a couple of seconds, I've gotten the outcome of the prediction. So I recommended some items. The one that was highest on the list was maybe the one that was predicted most to be likely to be clicked. But I clicked on one. So that one is the outcome of the prediction. It's the one I actually clicked on. And the ones I didn't click on, that's another outcome. It's a negative outcome, not a positive outcome, but it's still an outcome. So if I'm able to collect outcomes and I've already got my predictions, so we've got the predictions Q y hat and we have Q of y. They're the actual outcomes for the input features, Q of x. We can obviously measure the performance of the model. So it might be accuracy. We can say that the predictions were 98% accurate or 99% accurate. And we know that, for example, with credit card fraud, it doesn't really matter if you get 99% accurate for true positives, because if you got a lot of false positives, then people are getting suspected fraud on their credit card, whereas it didn't actually happen, and that's very annoying for those people. So you basically can compare the predictions with the outcomes, and in credit card fraud it takes a long time to get the outcomes, but in the recommender system they come very quickly. And if you're able to get them quickly, then you can measure concept drift in your system. And this is probably the best thing to measure, best bang for a buck, if you can collect your outcomes, and then you can compare them very easily with the predictions that were made. Obviously you'll need to have some sort of identifier like a primary key or a request ID that enables to join the outcome back to the prediction. So that's very important. But if you have, then concept drift will be the highest value metric that you can get in here. And without concept drift, it's great to have feature pipeline drift, because then you can reject bad data that potentially is being written. Operational feature drift will warn you when new data is arriving that maybe looks different to the data you've had up to now. And then label shift might tell you, well, the predictions being made by your model doesn't look like the predictions being made in training. So maybe you're predicting too much credit card fraud, for example. So just a summary of these different measures and why these ones in particular I've highlighted. Well, these are practical to measure. So feature pipeline drift, it's the distribution of a feature in a data frame that's being written to a feature group, and it's significantly different from the distribution of the feature group that's stored in the feature group. So HopsWorks will store, for example, descriptive statistics over features and feature groups, and you can use, for example, standard deviation to see if the new feature being written, if it's maybe 2 or more standard deviations from the existing feature in the feature group, well then you might say, okay, this is feature pipeline drift. And the same is true for operational feature drift. We just need to maintain a window of this inference data coming in. So it may be that you can take the batches of data that are coming in and say, well, that's my window. It's the batch of data that I want to score, and I can then check for feature drift between this batch of data that's being scored and the existing data in the training data set for the model that I'm using to do the scoring. And this is often been called covariate shift, by the way. But there's an additional assumption in covariate shift that the models, the predictions of a model given its input is kind of holds true. That means basically the model is performing as we expected, but the features are drifting. So it's easy enough. It may be the case that, for example, if you get small batch predictions, maybe let's say 100 rows, and you don't want to measure feature drift over that small a size, well then you'll need, what you should do in that case is store those predictions and store the features, and you could store it as a feature group in HopsWorks, and then when you want to compute feature drift in the operational case, you go to that feature group and say, okay, give me the last 10,000 rows, for example, or the last rows written in the last 5 days. And that hopefully that window will be big enough in which you can compare the distributions of features in that window with the distribution of features from the training data set for the model that you're using. The same is true for label shift. You need to store the predictions, and maybe you can do it with a batch, but if it's in the operational case, you'll need to just store them. Feature group is a pretty good place to store them. And then you can then compare those predictions and the distribution of those predictions with the distribution of the labels in the training data for the model. And then concept drift is great if you can collect the outcomes, and if the outcomes then just are significantly different from what the model predicted, you've got a pretty useless model and you maybe want to retrain. So that's kind of the main theory that we're covering in today's lecture, and I'm going to just move on and show some case studies for a couple of large internet companies. So Lyft are a taxi sharing company based out of the States, and they have huge volumes of data. They're kind of like a smaller version of Uber, not much smaller, but slightly smaller. And what they wrote a paper which is linked at the bottom. It's actually with IEEE Spectrum, or sorry. They wrote a paper, or in fact a blog, about how they do monitoring of their online models, which I found to be quite informative, so that's why we're covering it here. In their case, they said, for our online use case, in which we only validate a single feature vector at a time, an implementation with less overhead was required. So what that means is that when they're going to make an individual prediction, maybe it's related to, for example, how long it's going to take to collect a passenger or to arrive at a passenger, we're going to have these input features, and they're going to validate that single row or feature vector at a time. In that case, they found that the monitoring of this input features should be performed asynchronously, because the latency of the prediction needs to be low. And if you're going to do that in line, it's going to have an impact on your latency, which is more important to them. So in that case, you can do your feature monitoring asynchronously. And here's how you can do it, for example. So you can take the predictions made by your model in the model predictions log store. So this could be, for example, a feature group in HopsWorks. And in it, you can take, okay, for this model, we had these are the input features. These are the statistics of the features. And then we're running the model prediction logs for each individual model. We're computing the statistics over all the features to it. And we're looking for anomalies in features. So we have a feature anomaly detector. We can look at volume anomaly detection. We can have other anomaly detection. And you got prediction anomaly detection. So there's a lot of anomaly detection here. But that's quite a useful way of identifying when there's a problem with the data. And then you can basically dashboard these. So you put them in Grafana or some other system, and you can have alerts set up as well. This is pretty nice. They also have showed how they do performance drift detection. Again, it's all automated, and this monitoring framework that we talked about that they introduced, it is work, right? It's a defensive investment. It's basically, it's going to make shipping your new models slightly slower, but what it will give you is confidence in the models running in production operationally, that they're working as expected, and that the data they're making the predictions on is good as well. So the kind of things you can do here is you can see we've got a metrics query in SQL and a validation rule that you can find in JSON, and together this will be defined as part of your model configuration. And what you can do is you can compute the metrics and store them in a metric store and have monitoring dashboards for them. You can validate the data that's coming in against this validation rule. So it could be like great expectations, and store those results again in a monitoring dashboard. And if you have, for example, the likes of great expectation validations fail, you can page then people to say, hang on, there's a big problem with the input data. So Netflix, who are also a very large internet company that do streaming videos, they talked about how they do issue detection or monitoring in a paper at RecSysOps. So it's for recommendation systems. But some of the tips they give I think are quite useful. So we'll go through the first one. It says proper data logging. So logging the model's input and output for a sample of users on a regular basis for all segments of users. So in their case, they generate so much prediction log traffic, they don't store all of it. They just say, we'll store a sample. But we need to make sure we get all of the different segments of users so that the prediction logs are representative of all the users they have. Second thing that they said was that you should identify features that contributed to the unexpected model's output. So if you have an anomaly detected in your monitoring system, wouldn't it be great if you had some feature importance? It could be SHAP, it could be Lime, that will help you identify what the feature was that contributed to the unexpected model output. Then you can potentially go back and look at that feature and maybe all the way back to your feature ingestion pipelines and find that, hang on, I need more validation there. You can also use anomaly detection methods to identify features abnormal. I mentioned this already. So you've got Lime and SHAP, and they can be used for feature importance. There's also feature sensitivity frameworks out there. And then number 4, if all the inputs are as expected, everything's good, we need to investigate the model and find out the root cause of its output. So then you may need, in some cases, particularly if you have deep networks and you're not sure what's going wrong, you might need to visualize the layers of a deep network. You might even have to visualize the structure of a decision tree. Sometimes you train models and particularly in deep learning networks, you can have vanishing gradients and ReLUs that die and things like that. And you want to just, sometimes you need to actually just then visualize the different layers to see where the problems are. You can also train models to be robust against, problems with input data. So you can, if you've got timeouts or corrupted data, you can make the models robust against those kind of transient errors as well. Finally, in number 5, you can make a model also robust against missing data. We'll see, sets of values of that feature. It might be missing in your training data to make sure that the model can handle that. There's some techniques you can use like that, missing data, corrupt data, and so on that you introduce in training to enable the model to have support for scoring samples when feature values are either missing or incorrect. And there's a reference down there to the Netflix blog about this. So that's it. Thanks for listening. We had a lot to cover here. In the lab, we're going to look at versioning of feature groups, versioning of feature views, versioning of models, using Pytest to run unit tests for feature logic, we look at great expectations for validating data that we write to feature groups. A lot of good practices that you can introduce into your MLOps effort. Thank you.